The question is, how are you feeling today or right now? Okay, Alhamdulillah, I see that you are doing okay. The not so good. Arif Azman, can you share with us, if you don't mind, why you're not feeling well? Arif? Yang ni tak boleh type ya? Ada yang direct message, rahsia-rahsia je, nak cakap baik pun tak nak share.
Saya demam, Prof.
Oh, demam, semoga cepat sembuh. Kalau nak baring pun okey. Tak ada masalah. Alright, if you, sebab demam pun kadang-kadang tak boleh fikir, pening. That's one good thing about having online class, right? Then it is recorded and then you can join in again. Kalau first time you cannot concentrate because of certain reason, you can go back if you miss anything, something that we cannot do if we do it physically. But the interaction, physical interaction is totally different, right, from this. So that's why I'm trying my very best to deliver the lecture like physical. I think if I'm the student, I would like to see my teacher or lecturer explain on the board. So for a lecturer, I want to see your expression. I cannot see any expression if the screen is just the name. That's why. Okay, I don't mind if you want to drink, you want to eat while this. I didn't say that tak boleh lah, right? Kadang ada student yang need to go outside. We have macam-macam lah, but having you here, it's good enough. Having you here and having you to join. And itulah kadang-kadang pun kita kena jaga kesihatan lah ya, because we still not safe, although ada ni pun injection dan sebagainya kan, still, and Omicron masih berluasa lah. There are also new cases around. Anyhow, let me continue. Yesterday we saw and proved that a set is a group, right? And you can try some more examples, but I mentioned about uniqueness of the identity and inverse. Okay, so sometimes the question is very, very short. The question is short, but the answer might not be that short. Something like proof, or sometimes you have to show that the identity in a group is unique. Okay. I'm not sure if it's in the notes or not, but that is a very normal property also. This common, the property that you have to know and you know how to prove it. So to prove, okay. We have to have a group, right? So let G be a group and E1 is, I put N identity because we have to show it's unique, right? It's an identity in G. Okay, to show something is unique, we have to assume that it's not unique there are two of them, then you have to show they are equal. Okay, this is by contradiction. Yeah, prove by contradiction, assume is the other way around, and find a contradiction. So suppose E2 is another identity in G. Okay, so the task is, I put in bracket, this is what we want to do. We want to show that whatever other identity that we have, it has to be equal to E1. Okay, so not only in this class, maybe in the future, you need to show something is uniqueness. So this is the way to show it, right? Otherwise, how do you prove something is unique? Something is not more than one. Then you use the definition to do somehow to get E1 equals E2. The computation is normally not difficult, but how to start with, right? Okay. Since E1 and E2 are the identity in G, okay, because we assume, right? So for all A in G, okay, the property, right? A times E1 is equal to E1 times A is A, and A times E2 is E2 times A is A. Okay, so this is what we have. Now you can see, right? You can see how you can show E1 is E2. It's quite straightforward, right? So since A is equal to A, you can take this side or you can take this side to be equal. Yeah, there are two ways. Just take one. So from here, A times E1 is A times E2. Can somebody help me how to get to the next line? What do you do? Nizam, are you here? Muhammad Nizam?
Yes, Prof.
Yeah. How do you get from this line to the next one? How do you simplify?
Bring to other side.
Wah, dia kucing. Dia pun nak belajar. How do you bring to the other side? What do you want to bring to the other side? You see, if you have this like this, what do you do? Normal is that, right? How do you simplify this one?
Bring to over. Will be
Oh, why do you want to bring 2 over? You will divide by 2, right?
Yes.
You just number, right? So you get X is Y. This is just a number. Okay, but this is not a number, right? You cannot divide by potong-potong. Apa potong-potong? You cannot divide by A. These are just elements in the group. Okay, what do you have to do? What do you want to bring over? What? Okay, anybody can help Nizam. How do you get rid of this AA here? Any suggestion? Inverse, yes. Inverse, because this is a group, okay? This is actually the inverse, right? The inverse of 2. What we did here is actually we multiplying by a half. Kan, dulu kita belajar potong, divide. But this is actually multiplying by the inverse. The inverse of 2 is a half. Tak perasan kan? So this one, you multiply both sides at the same side with the inverse. Okay, why we do have this inverse? Because G is a group. So there is an inverse. Okay, so you multiply both on the left-hand side You can do this, right? Because you have the binary operation. And what is A inverse times A? What is A inverse times A? It's new lah. E, right? A inverse times E, yeah? We use E or the identity. Whatever identity lah, E1 ke, E2 ke, doesn't matter. Okay? Just call it E, right? Because now we have two E, right? E1 or E2. I just call it E. This is also, whatever that is an identity, E1 or E2. And the identity times E1 is E1. The identity times E2 is E2. So if you have more than one identity, they have to be equal. Even if you do this one, if you choose this one, you will multiply A inverse on the right. Okay? So you have this, thus, don't forget to write the conclusion. Thus, the identity is unique. Okay. All right. Next, we show that the inverse is also unique. Okay, the inverse is also unique. This is theorem 6.6. Each element has only one inverse. Let's try to show this. Show that the inverse of each element in a group G is unique. Show that the inverse of each element in a group G is unique. So take an element, right? And then take one inverse, and then take another element, say it's another inverse, right? Use the property and show those two inverses are equal. Okay, so it's the same idea as the identity, but using a different property of the inverse. Okay. Malas pun tak padam dah kan? Okay, easy. Okay, let G be a group and A is any element in G. Okay. Suppose B and C. Suppose B and C are two inverses of A. Or you can say, suppose B is an inverse of A. You know it exists, right? Because it's a group. And C is another inverse of A. Okay. We want to show B is C. So if you have any other inverse at all, then you can use the same thing and show they have to be equal. So you only have one inverse. Okay. We have, I can write like this in a class, but when you do your PSM next year, Project Sarjana Muda ya, for FYP, you cannot use we, yeah? Cannot use we in any inside your report. Okay, in class is okay, in the notes is okay. Okay, we have these two inverse. So A times B is B times A is E. I add here, and E is the identity. Yeah. Okay, we have to have the identity. So we have, since B and C are two inverses of A, so we have A times B is B times A is E, and A times C is C times A is E. Do you see the way we write? And you can see like before, right? It's very easy to show B is C, right? Like before. Because E is equal to E. So from this, you can get AB is equal to EAC is also equal to E is equal to AC. Okay, don't divide and potong-potong. So you multiply whatever the inverse exists, whether it's, you can multiply by B or you multiply by C, right? Or you multiply by any of those because, okay, say I multiply by B, yeah? If you multiply by B here, right? So B of A is E. So E times B is B. Okay. Conclusion, thus the inverse is unique. If you multiply also by C here, it's also okay. Because CA is also E. All right, okay. I also use actually theorem 6.7 in the proof. Okay, cancellation property. You multiply. So how to show cancellation property is to multiply both sides at the same side. Don't multiply one on the left, one on the right. No, if you multiply here by the left, multiply here also on the left. Don't multiply here on the left, that on the right. Numbers, we normally do that because numbers, they commute, right? Doesn't matter. But in this group G, not all groups are abelian. So make sure that you multiply on the right side. Okay. Next, we have to look at a subgroup. Okay, a subgroup. I should create a definition of a subgroup because it's, yeah, definition 6. I make it, Shiham, you help me note this. Definition 6.8. In my notes is page 195. Okay, call it a subgroup. Okay, so the next one is subgroup. Subgroup is like you have set and subset, yeah? Okay, so subgroup. A subgroup is, okay, let G be a group. And H is a subset of G. Okay, so if you have a set G, H here, we call it subset, right? So we have H is a subset of G. Okay, the first one, H is closed. Okay, H is closed, meaning H1, H2 in H imply H1 times H2 in H. When I said times, it can be a star, whatever the operation, yeah? And the operation in H has to be the same operation as in G. Okay, so G be a group and H is a subset of G with the same operation. You don't change the operation. So H has to be closed. First, it has to be contained inside. It has to be, the second one, it has to be closed. This one, E of G has to be in H. You know, G is a group, so it has an identity. But the identity has to be in H. Cannot be here, right? Cannot be outside. So the identity of G is, the identity of H has to be the same because it's a subset, right? And the same operation as the identity of G, but it has to be inside, cannot be outside. Okay. And also it has to be closed under inverse. If there is A here, okay, if there is A here, A inverse has to be in here, cannot be outside. Okay, so you can now, once you get a new definition, if you want to really understand the definition, try to come up with an example. Okay, and try to come up with a non-example. So you will understand why we have some limitation in some example. So you see, if to be a subgroup, H has to be a group by itself. Okay, it has to be a group by itself. And we use this notation. H is not less than, yeah. This is not a number. This is the symbol for a subgroup. It can be equal to G, but it can be not equal to G. This is a subset. Okay. All right. Let's look at one example. Nurul Diana, are you here?
Yes, Prof.
Okay. Can you give me an example of a group with an operation? Just give me an example of a set, which is a group with the operation. Apa dia?
Integer.
Saya guna bracket. Right. Integer with
Plus.
operation plus. Okay, good. Scary kan pensyarah panggil nama? But untung sebenarnya yang dipanggil nama, you will remember your answer. Doesn't matter kan salah. Kalau salah lagi ingat. Okay. Alright. Then you're thinking, okay, this is a group because, oh, you realize we don't mention about associative, right? For subgroup, because it's already a subset in the whole group. So operation is the same. So associativity also stays. Okay, that's the only thing you don't need to check for subgroup. Okay, just need to check others because it might go outside. Okay, so what's the identity, Nurudiana? What's the identity of this? A plus what is equal to A?
A plus 0.
0, yeah? The identity is 0 because A plus 0 is A. What is the inverse of A? A plus what is equal to 0?
A.
A plus what is equal to 0?
2
2 plus what is equal to 0?
So,
Negative, right?
ah.
These are all integers. Okay, so you have to think about the property. What does it mean by identity? Identity is A plus identity is A, right? And then you can easily think about a number. And the inverse means A, because the operation is plus, before this I said A times A inverse equal identity, right? Because the operation is plus, so A plus A inverse is identity, which is 0. A plus A inverse is 0, so A inverse has to be negative A. Like 3 plus 1 is 0. Senang nak fikir kan? Okay. Now, okay. So now I have this Z with this plus, right? All right. Shakir, Ahmad Shakir, are you here?
Yes, Prof.
Okay, give me a subset of this. Subset, saya tak kata subgroup, subset.
Subset.
You have integers, all 1, 2, 3. What's the subset?
Rational number.
Rational number. This is a subset of rational number, right? Rational number is bigger, right? This is Q. Inside is Z. I want a smaller subset of Z. Anybody wants to help? Syakir, nanti dia kena belanja. What's the subset of Z? Yeah, Jimpa, you want to help?
Whole number.
Whole number. Akmal. Whole number, apa simbol dia?
W.
W, Kita jarang guna W.
Natural number.
N lah, N. N with also plus, right? So N starts with?
One.
Your N starts with?
1.
1. Okay. Certain books, N starts with 0. But as I mentioned, because our principle of mathematical induction in N starts with 1, yeah? And just now, Z, okay, I put like this, right? So if you want a subset, find a smaller set. Shakir, you understand? Find a smaller set.
Yes, Prof.
Can you give another one? Dah faham tu? Can you give another subset? You can say in words if there is no symbol for the subset. Banyak kan? What is this? The set of positive integers, which is equal to this, right? Or you can have the set of negative integers. Okay. Negative kan? Ke sana. Or we can have the set of, I call it P, of prime numbers. Prime numbers. What are prime numbers? 2, 3, 5, 7, ... Prime numbers. Banyak lagi kan? But not rational number. This is bigger. You want a smaller one. Or we can have like 2Z, right? 2Z will be all even numbers. Okay, even numbers. Or you can have 3Z, a multiple of 3. Okay, and ... you can have KZ, multiple of K. Saya tengok, saya pin sekejap. Saya punya. Let me see, check my. Okay. Nampak Okay, make sure it's clear. Alright. Okay, because I tengok view. I look at the view gallery tadi. Okay. All right. Okay. Now we have quite a number. Now next question is, okay. We have 1, 2, 3, 4, 5, 5. Now think and decide whether each of these is a subgroup or not. Okay, if yes, it has to satisfy all three properties. If no, tell me which property it does not satisfy. Okay, ada 1, 2, 3, 4, 5. Question is, decide whether the following subsets are subgroups of Z plus. Meaning the operation has to be also plus. Okay. So what's the answer here? Yes or no? Type in the chat. Is it a subgroup? Yes or no? Laju sikit, laju sikit. Is it a subgroup? Yes or no? You're not sure, easy kan? It's just yes or no. Hantam lah, yes or no. Okay. Let me see. Atif, you are the first one that said no. Atif, Muhammad Atif.
Yes, Prof.
Why not?
Because 0 is not in here.
See this? You have to know this first and check. Yeah? Okay. 0 is not in here. So it cannot be a subgroup, right? So N is not a subgroup of Z and the plus because it has no identity. The right way to write it, you cannot say 0 is the identity, but it's not inside. That is no identity, yeah? But if you say that, I will accept that too, because I know you understand. Because it has no identity. And the right way to say is that there are two ways people write it. Okay, A plus E equals A shows E is 0, but 0 is not in N. Okay, this is one way, easiest way actually. You solve this, this gives us E is 0, but it's not in N. Or you say there is no E in N such that A plus E is E. That is another way to write that. Kalau dah tak ada 0, you don't need to mention about the inverse. It has to be the 0 first. Okay? Soalan tu, okay? Okay tak? Okay. Faham Alright. Okay. Okay. Page 2, okay ke tak? Okay. Macam mana kalau nak letak? Tak okay. Oh, there is a 3 dot. Oh, ada. Tengok tu kalau tak okay. Terbalik. Tertongging dia punya. Okay, jangan main-main. Jangan cuba-cuba. Nanti kata tak okay. Alright, second one. So this is not, yeah? Okay, what about this? Yes or no? Jawab. Check. For this one, yes or no? Senang kan? I hope I don't say any yes. With the same reason, yeah? Because 0 is also not in here. Okay. Now, the third one. Sama this one. Z minus is not a subgroup. And the plus because it has no identity. Okay, what about this? The same, right? Because 0 is not in there. And before you even check for 0, it is also not close. Maybe the question asks, decide whether it is close, right? 2 is in here, 3 is in here, 2 plus 3, 5 is in here. Then you say it's close. No. True for a pair does not mean true for all. So you have to check again and again and again. Like these two, right? 3, 5 in P But 3 plus 5, which is 8, is not in P because 8 is not a prime number. So it's not close, right? So if you say that that is the reason, yes, okay, can be accepted. If you mention that 0, there is no identity, okay, that can be accepted for this one. Prime numbers. Now, 2Z. 2Z, yes or no? Answer in the chat. Okay, let me check. 2Z. Yes or no? Yes or no? Yes or no? Come on. Is the 0 there? Yes, right? Is the negative there? Yes. Okay. Is it close? If you take 2 elements inside, x, y in 2z, right? So you can write x is 2a, y is 2b. A, B in z, right? So x plus y is also 2a plus b or 2c. Yeah, so it's close. Don't pick any two and show. You have to show in general. Okay, so the first one you have to show it is close. The second one, the identity 0. And the third one is for any x which is equal to 2a. The negative x, the inverse is negative 2a, also in 2z, right? Okay. 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 Last question. Okay. So this is okay also because it's the same, right? This is also okay because it's just k. So you just replace with k, k, k. And when k is 0, you get the identity, right? It's you always get the identity. This k is in integer, and the negative is also in part, right? So they're all okay in general. It is a subgroup. Okay. My last question. H equal to Z plus union 0. Yes or no? This we call non-negative set of non-negative integers. Yes or no? Okay, I see some answers. Why not? Write your answer there. Why not? Okay. Since not all elements in H have an inverse. identity, right? 0. And what is the inverse of 0? The inverse of 0 is 0. So only 0 has an inverse, right? The rest, they don't have inverse because there is no negative. Okay. Not all elements in H have an inverse except for 0. That's one way to do it. But the easier way to write is 1 have no inverse. 1 has no inverse. Because -1 is not in there, right? 1 has no inverse, done. Not true for 1 means not true for all. Yeah. If you said there is no inverse, that's not true because 0 has an inverse, but not the others. Okay. Clear, right? So you have to think first and see to have an inverse, to have an identity, you have to know the elements in the set, right? Okay. Any question? Is it okay? Okay. Okay. Yeah. When you said inverse does not exist, it has an inverse for 0. Right? The inverse does not exist for all elements. Okay. So you have to write carefully. Inverse does not exist for all elements except for just 1. I can give you so many different other, right? The set, and I can also change the operation. All right. If we have time, we'll go through the exercises also later. Okay, next would be to introduce cosets of let me see. There's some examples that you can go through and see whether you can understand those. Yeah, example 6.22. So if you have like complex, right? There is an R, there is a Q, there is a Z, there is an N, right? So these are subgroups from before under the set, but if you do plus, they all becomes a subgroup, yeah? Under plus. They're all subgroups. Apa ni? No, this is wrong. Terbalik ya. I want to do this. Okay. Balik pak yang kecil lah. Okay. But you cannot put N here, right? This is true, but it is not a subgroup. Right? Just now there is no 0 under addition. But you can put 2Z or KZ. Okay. Okay. Right. Then you can go again through the okay, example 6.22. Then there is a 5Z. Okay. Oh, okay. Okay, example 6.26. Example 6.27 is this one. Okay. All right. They can also give you a question of Kelly table, okay, given a subset of a group. Okay, now cosets, yeah. Let G be a group and H is a subgroup of G. Then H is a left coset of G, A plus H is equal represented by A in G and defined to be A plus H, H in H. Sometimes people use the word coset differently. Cuma perempuan pakai coset. No, not that coset. Yeah. Or you can have any operation star right. Okay. One minute is too fast, yeah? Okay, let me check a different kind of groups that you need to know. Do you have to know about, okay, Z plus, okay. So if you have, for example, G is the set of integers under addition. So again, I will write okay, and you have to choose one H to be the subgroup. So suppose H maybe 3Z. Yeah, this is the 0, 3, 6, 9, and then the negative 0, negative 3, negative 6, negative 9, dot, dot, dot. So I start with negative 6, negative 3, 0, 3, 6, dot, dot, dot. Okay. So you have to find the coset or the left coset of G represented by an element. So first is you start with the group or the subgroup H, which is this. Okay. Then what you do is you slash out or you cancel the element in G, which is already element of H. So I cancel. And there are some others. The next coset, you have to take the element which is not cancelled yet in G and to add up to the element of H. That will be our second coset. So I take 1 plus H. We don't add element to a set. We add element with an element inside the set. So what you do is you adding 1 to each of the element in here. Okay. So 0 plus 1, wait, I add this one first, negative 5 plus 1, negative 2 plus 1, 1, 4 plus 1, 7. they're always 3 apart, yeah? Right? If you want to add one more, there will be 10 and so on, right? Then you cancel. You will cancel actually the next one. And then the next one is that. And the next one, which is not cancelled, will be 2. 2 plus h. 2 plus h, not 2 plus this. So 2 plus this is -4, -1, 2, 5, 8. And then when you look at this, and then you look at this and you want to cancel, you see that you are actually canceling the rest. This one, -1 just now comes from, where was it? Oh, here, right? So -2, right? So end up that you will cancel all, meaning if you take the next one, you have 0, right? This is 0 plus. 0 plus h is h. 0, 1, 2, 0, 1, 2. If you take 3, you add up to this, you will get back this one. Because 3 plus this will be 3, 6, 9. So this is actually equal to whatever you see here. 0 plus h is 3 plus h, 6 plus h, and so forth. Okay, so that covers everything. This is 1, 4, 7. So 1 plus h is 4 plus h. This is 7 plus h. Okay, and 2 plus h is actually equal to 5 plus h, and so forth. And also the negative part. All right. So this is the list of all left coset of h in G. So the left coset, you will write h, 1 plus h, 2 plus h. So only 3 cosets. Okay, you see Z is infinite, h is infinite, but the coset, there are only 3 of them. If I change 3z into kz, you can have k coset. Okay, and then you can have so many numbers of k. So this is what we mean by coset. Okay. If you do a right coset, it will be the same. Yeah. If you do right coset, it will be the same. You add on the right, because sometimes it's not commutative. If it is commutative, a plus h is h plus a. Some groups, they are not commutative. So you multiply left and right, it will be different. Okay. So this is left coset. The same thing with the right coset. Okay. Let's look at the notes. Yeah, I have that. Okay. And also 4k over there, you will get 4 coset. Okay. Oh, there is a Z6 there. Okay. Let me introduce a common other group. Yeah, I did not introduce this before, but let me introduce ZK. ZK is a group under multiplication modulo k. Okay, what does it mean by ZK? ZK starts from 0, 1, 2 until k minus 1. So ZK is 0, 1, 2 until k minus 1. And we don't normally go Z1 because this is just, we call it a trivial group or subgroup. It's just that one. Yeah. Okay. Okay, Z2. Kita tak payah banyak pun tak apa. Okay, 0, 1 is always start with 0 and it ends with K minus 1. Then you get Z3, 0, 1, 2 until you have ZK. Okay, what does it mean by what is this? Addition. Addition is not multiplication. The multiplication operation is addition modulo n or modulo k. Okay, what does it mean? Belajar modulo kan before this. It's like a clock, right? A clock is modulo 12. So when you go 13 is 1. You take the remainder, yeah? Okay. So also another one. Okay, this is trivial. We don't want to talk about something trivial. 0, 1, if you do the Kelly table, okay, fill in the Kelly table. This one, I use this as the addition modulo K, all right? Okay, so you know the identity of ZK of n, normally we say Zn. Okay, normally we say Zn, but doesn't matter. Is always 0 because it's under addition, right? For numbers. And for the inverse, if A is in ZK, A inverse is K minus A. Because when you add right, K is 0, right, modulo. Okay, because when you add the inverse with this, you get. Okay, so fill out the blank. Fill out the blanks. Or fill in the blank. Fill in the blank. For that. So let's do for 2, 3, 4. This is Z3. Then Z4. Fill in the blank. So Z4, Z3. Okay. Easy, right? Just add 1 plus 1 modulo 2 is 0. 1 plus 1 is 2. 2 modulo 2 is 0. 2 modulo 2, 0, or 2 is 0 mod 2. Because 2 divided by 2, 1, 2, 0, right? So the remainder is 0. Okay. Now here, when you add 0, because it's the identity, you just don't need to add, right? When you add 1 plus 1 is 2, 1 plus 2, 3 is 0, 0, 1. You see, it's a group because all elements are inside, and you can see the inverse also, right? The inverse of 2 is 1, the inverse of 1 is 2, because 1 plus 2 is 0, and the inverse of 1 is 3 minus 1. Oh, terpadam. Okay, so this one, 1, 2, 3. 0, 1 plus 1 is 2, 1 plus 2 is 3, modulo 4, yeah? 0, 3, 0, 1, 5. 5 is 1 modulo 4, and the remainder is 1. 0, 1, 2. Okay, so we are done with a group under addition modulo K. Okay. Okay. Now subgroups of Zn. Okay, actually for Zn, we have subgroups of certain order. For example, let me see for Z4 subgroup, I can have 0. We have many subsets, right? You know, if you have 4 elements of this, you have 16 subsets, right? But not all subsets are subgroups, right? You have subset 0, you have subset 1, you have subset 2, you have subset of 3, 4 already, and you have subsets of order 2, 1, 2, 3, 4, 5, 6. Then you have subsets of order 3, 0, 1, 2, 0, 1, 3, 0, 2, 3, 1, 2, 3, right? And then you have the whole 0, 1, 2, 3. So you have many of the subset, but they are not all subgroup. Subgroup needs to have the identity, it has to be close, and the inverse, right? So if I choose 0 and 2, this is a subgroup. Easiest way is to do the Kelly table. And you get 0, 2, 0, 2, 2 plus 2 is 0 modulo 4. So you know that's the identity. 2 is the inverse of 2, 0 is the inverse of 0. It's close, so this is a subgroup. If I want to say K, definitely not a subgroup because 1 is not close, 1 plus 3 is 4, 4 is not in there. And also there's no identity, right? So it's not a subgroup. So this is how you come up with a group, then a subset, and then show that it is a subgroup or not. Once you get a subgroup, actually the subgroup of this is a subgroup. It's called a trivial subgroup. It's always just the identity is always a trivial subgroup. So every group has a subgroup. And itself is also a subgroup. G is also a subgroup of G. Okay, so we have what we call a trivial subgroup. And we have improper subgroup. If you have H, a subgroup of G, but not equal to, it is called a proper. Okay, if H is not trivial, if this is not trivial, we call G a non-trivial. Okay, if this is trivial, we have a non-trivial. If the element of H, there's one more, at least, not only the identity. Okay, so for Z4, this is called the trivial subgroup of Z4. This is the proper non-trivial subgroup of Z4. Z4 is the improper subgroup of itself. Okay. And you don't have any, only 3. The trivial, this one, and the whole one. Okay. Then I can ask you about the left coset for Z4. left coset of H in Z4. So first we have H, right? Which is actually 0 plus H and 2 plus H. Okay, next one, you cancel 0 and 2. Next left is just 1 plus H. So you add 1, you get 1 and 3, which is actually equal to, oh, already have. Okay. So you cancel 1 and 3, done, yeah? So you only have 2 cosets. The number of cosets is actually the number of element in G divided by the number of element in H. There's 4 elements in G divided by 2 elements in H. 4 divided by 2, you have 2 cosets. So you have 2 cosets. So we have cosets is H and 1 plus H. 2 cosets only. Okay. Next, I want to actually explain this example in the book, in the notes. The Z6, yeah, example 6.27. Okay, 6.27. Z6. Z6. Let's do this. Okay, G is Z6, which is 0, 1, 2, 3, 4, 5. And H is 0, 2, 4. You might need to show that this is a subgroup. Okay, so the easiest way is to write out the multiplication table. This is addition modulo 6, 0 to 4. Then you show that all elements inside the table are all elements of H. 2 plus 2 is 4, 2 plus 4 is 6. 6 is 0 modulo 6, 0. 4 plus 4 is 8, 8 modulo 6 is 2. So you see all elements are elements of this. So H is a subgroup of Z6. And also it's closed, right? Closed. The identity is 0 and the inverse of 0 is 0. The inverse of 2 is 4. The inverse of 4 is 2. And the coset, the first one is H, right? As the coset. So you cancel 0 to 4. The second one is the second coset. You add to that 1, 3, 5. Then you cancel 1, 3, 5. And the one left is 2 plus H. 0, 1, 2. Hey, I cover all. 0, 2, 4, 1, 3, 5. Oh, okay. 0, 1, 2 is already in there. Okay. So only 2 coset, yeah? 2 coset. Oh, yeah. Why? Because the number of cosets, we call it the index of H in G. This is what we call this symbol. Okay, the number of cosets or the index of H in G is using this formula. This is the number of element in G, the number of element in H, which is just 2. So we have 2 cosets, 1 plus H and H. And there's another subgroup that I can give for this, call it K, yeah? This is another subgroup. Just now we have only one proper subgroup, but this one I can have 0 and 3. Okay, and with this one, you can have 3 cosets because 6 over 2 is 3. So for K, you can have K, 1 plus K, 2 plus K. That you can try yourself. Okay, that actually cover that one. The last part is on the normal subgroup quotient group. I will continue next time. Too many things then pening pula nanti kan. And also the last part is isomorphism. Let me see the question. Over the weekend, you can go through the previous chapter, okay? Do all the exercises. And also for this one, what's chapter 5 last time? Boolean, right? Boolean, chapter 5. Yeah. Chapter 5 is Boolean. Next Thursday will be the quiz for Boolean. Then we'll have a test too, right? Okay. So make sure you do all exercises. And in the next class, you ask me if you have any question. For this one, you can already try and do exercises until number 16. Okay. If there is any typo, you let me know or let Hannah or Shiham know. Like number 16, I see a capital B supposed to be a small b. I'm not sure. This is maybe the old one. Okay.